Okay, guys. So I think we can start now. We are already 4 minutes ahead of time. So please let me introduce you today, Vittorio Memmolo. He's coming from University of Naples, Federico II, and he's a professor on aerospace, aircraft structures, and astrodynamics. And his research focuses on the design and of composite structures, structural health monitoring, and these kind of structural things that are trendy nowadays and of aerospace interest. So the menu would be like a presentation of half an hour or so, and then we can have some 10-15 minutes of for questions. Okay. So without further ado, please, Vittorio, the floor is yours.
Thank you very much. Thank you, Alberto, for the introduction, and thank you for coming to you all. As said, I'm Vittorio Memmolo, assistant professor from University of Naples at the Department of Industrial Engineering. We are the former Department of Aerospace Engineering, in which there is this group, Aerospace, that you can see from here, Aerospace Structures and Material Group. I will basically touch some of the activities we are conducting on SHM, structural monitoring, and I would like here also to get credit to some of my colleagues with whom I'm working basically since more or less 10 years. My intention is actually to move from first some methodological aspect to then put the accent on certification related challenge when we are talking about structural monitoring in aviation. What I will introduce here is just a brief introduction about myself, the motivation for having SHM within the aviation and specifically for the airframe, some approach based on guided ultrasonic waves, which is the methodology, the methods that we mostly use based on ultrasound, some challenge for industrial deployment, specifically within a regulated environment, which is aerospace environment, before giving some concluding remarks and hopefully a brief discussion with you for what I have just introduced. Just about myself, as Alberto said, I am assistant professor in Naples. This is just a few overview. I actually got the Bachelor of Science, Master of Science, and PhD in Naples. Then I traveled a little bit around, but I was mostly working there since 2013. This is basically my, let's say, track. Starting as postgraduate intern, research assistant, doctoral scientist. Then I moved to Fraunhofer for a while, back to Naples, then back to Germany. I am in love actually with Germany. I spend a lot of time there at Fraunhofer, Frankfurt University, BAM, which is a Federal Institute for Material Research as well, Frankfurt University, and DLR recently, which is not mentioned here. This is actually an overview of what was my career related to SHM. Actually, the life motive is not SHM, but ultrasound. We started using ultrasound in 2010. Ultrasound, probably some of you is familiar with ultrasound for non-destructive testing. The concept is very similar, but adapted, of course, to having a system permanently connected and attached to the airframe. We moved from some European project where we tested SHM on horizontal tail, full composite especially, applying also to maritime problems, and moving to hydrogen. Also for hydrogen, we need to monitor structures which are not specifically aerospace, but sometimes just pipelines, but still the SHM can be imported there. Then we extended our competencies using ultrasound, specifically actuator, for something that is a little bit more exotic, let me say, hydrogen production by water, so sonolysis using ultrasound as well. The process is very similar. You still use ultrasound to activate something in the structure, as we will see later. And now we are moving to, let's say, higher TRL, but also to making the system more integrated, which is the reason why the accent at the end will be posed to certification aspect, because wherever you want to increase the TRL at a certain point, you have also to qualify or certify your system. And of course, now we are going very deep into AI, which is, I will have to omit today, but if you have any curiosity, we can discuss further. Why SHM? SHM is like, as I said, structural monitoring is a little bit different from non-destructive testing. With non-destructive testing, the aim is to test a specimen, test a part of an airframe, for instance, and verify whether there is a damage or not. This is usually already a scheduled maintenance activity. You already have, let's say, the input of where to test the aircraft, and this is an example. Sometime what happened, it can be, if we are considering metallic structure, it may happen that there is a crack, and the crack can propagate wherever and whenever you fly. You will fly in an aircraft full of cracks. I don't know if you are aware of that, but that's the reality. What is very important is to monitor the crack propagation, because otherwise the airframe could be unsafe. That's the reason why there are some scheduled inspection. The same happens for composites. Composites are more fatigue resistant than metallic structure for sure, but still they are very fragile with respect to impact. Whenever there is an impact, what it can happen is basically that you have an impact, especially in this part, in the front part, or on the lower wing panels. And if you have a composite, this is a non-destructive inspection based on ultrasound. What you can have is that all the structure is intact, but at the place, especially when there is an impact, there is a big damage. And if you inspect the composite through the thickness, there is a big failure. So all the composite, let's say, laminas, they are disconnected together. This is very critical because whenever you are supposing to work with a pristine structure, that you have a big damage and the residual strength gets much lower. This is the reason why non-destructive testing is something like very important, especially in damage tolerance, design and maintenance philosophy, but it's very expensive. Basically, whenever you are designing, especially a composite structure, damage tolerance approach wants that wherever you have a specific damage that can be detected on production, usually a bigger damage can be detected during operation in situ, which is much bigger than what you can see from the operation, after the manufacturing. Between these sites, which is the minimum detectable damage on site during the lifetime, and the maximum allowable damage, you need at least, by certification authorities, you need at least to have 2 following inspections, because there is always the possibility that you cannot detect the damage. In addition to that, you have to demonstrate, especially for composite, that the capabilities after impact, like a damage like that, under compression, are still satisfied until ultimate load. And you don't need to have delamination grow among the 2 inspections that we have seen here. Otherwise, you have to replace or repair the component. This is very demanding from, let's say, maintenance point of view, and that's the reason why SHM comes into play as a key-enabling technology. SHM can be basically seen as an extension of non-destructive testing, where you don't have an equipment with which you inspect the structure, but you have a number of transducers permanently installed on the structure, which are used actually to retrieve information about the current, the actual structural state. And we can use basically SHM, when we are talking about the SHM, we can use as an alternative method of compliance to non-destructive testing, as an input to condition-based maintenance, as a design enabler. Here, basically, we replace the NDT inspection with some SHM interrogation, so you use the data from the sensor to understand whether there is some damage or not. As input to CBM, basically, we want to move from a scheduled inspection approach to a predictive inspection approach. So you basically made the maintenance activity whenever you actually know that there is a damage or there is a high probability to have a damage. As a design enabler, that's basically our dream for anyone who is working in SHM, the idea to make less constrained the design of composite structures, because they are actually, especially when we are talking about knockdown factors, is very hard to deal with this type of damage, which are barely visible impact damages. On the time, of course, design enabler is very, let's say, far from today, but today we are mostly discussing about SHM as an alternative means, or a method of compliance to NDT. And basically, whenever we are talking about maintenance inspection, we are usually discussing a very long process which starts from the captain or the first officer that is doing the turnaround around the aircraft to check if whether there is something that doesn't work. If everything is okay, then usually you fly. Otherwise, you ask for a, let's say, level 1 NDI inspection, which is available at every airport. If still there is usually the detailed inspection or detailed visual inspection. If something is considering to be very risky, then you have the level 2 NDT inspector that should come, and this is not available everywhere. When we move to this phase, actually, we are already, as an operator, spending a lot of money before understanding if we have to repair or we can release the aircraft. All these aspects like operational visual check, functional check, detailed inspection, and special detailed inspection, they increase a lot the downtime. Of course, they produce a lot of downtime because the aircraft is on the ground and can be strongly reduced by integrating SHM as an alternative method of compliance to NDT. The idea is actually to move to this maintenance approach to the second one, where we have basically an automatic system, which is based on SHM, that can, in an autonomic way, ask for the repair or release the aircraft. This can reduce strongly the downtime, and then by reducing the aircraft on the ground, basically. When we are talking about SHM, we are not talking about scheduled inspection or just making more economical, cheaper the maintenance procedure. We are also talking about improving their worthiness. This is an amendment to a service bulletin of the FAA to the Boeing 737, where basically they found a big problem to the pressure bulkhead on the rear end of the aircraft. Specifically, the bolts of the rear end were affected by unexpected cracks during the lifetime. This means that basically whenever you have a possible crack that is increasing, you have to inspect the bulkhead. And the problem was that the maximum crack dimension, according to the certification authority, acceptable was 1 millimeter. 1 millimeter, it means that you are below the washer, so you basically have to completely dismount the pressure bulkhead, which is very, very time consuming. Also for this type of application, whenever you are not considering from the design a specific problem, SHM is a good candidate as an alternative method of compliance. And in the amendment was already mentioned, probably for the first time, to consider alternative method of compliance to NDT, which actually reactivated a little bit. It was 2022, the research activity around SHM. What we have developed during the last year is basically a multi-level SHM, where basically the idea oriented to composite structure, the idea is that we can monitor the cause of any damage, which is the impact, so impact localization, here, an event detection. We can more or less reconstruct the presence and detect the presence of a damage, then probably localize also try to assess the severity of the damage itself, and also check how the system itself is working, so the SHM system, not the airframe. Whenever you have all this in mind, you can say that SHM as an alternative means of a method of compliance with autonomic check can be, how to say, frozen around the methodology that you have implemented. And what I will show you today, before moving to reliability aspects, so industrial deployment, will be just an introduction to a global approach that we have developed and a local approach to size the damage that is occurring. Without diving too much into the details, but if you have any curiosity, of course, we can discuss later. The first important aspect is why we use guided waves. Guided waves are waves, elastic waves, propagating across the material, and they propagate according to the properties, the characteristic of the media where they are propagating. So what happens usually if you have a transducer in a place attached to a structure, and then you have another transducer that works as a receiver, if you activate here a deformation, a variable deformation over time at a frequency of in between 20 and 500 kilohertz, so quite high frequency, you can excite an elastic wave. The elastic wave is propagating through the structure and arriving at the receiver, and is arriving as this, over time, with a waveform that is like this. So it's, first of all, multimodal. You have different mode of propagation through the structure. Specifically, we identify a symmetric mode of the vibration of the structure and an antisymmetric mode, and then the waves itself are interacted usually with the edge or with the stiffness, wherever something, a discontinuity happens. The same happens when you have a damage. So what is the idea? That this wave propagation change wherever there is a discontinuity, which can be a designed discontinuity, like an edge, a stiffener, or whatever you have, a null, for instance. But when it's not expected, actually, there is a variation over time of this time signal. This is what we actually monitor, not considering only a couple of transducers, but a certain number of transducers attached to the structure. How we can work? We can work disseminated the number of transducers. If there is, this is, for instance, a plate, then you place a number of transducers, and whenever there is a damage, for instance, in a specific location, the wave that is propagating and finding the damage, interacting with the damage along the line of sight is actually altered. What we do is, starting from the signals that I showed you before, we make a sensitivity analysis. So we try to understand how it works when there is no damage to set a certain threshold, because there is a noise. You need to know which is the statistical threshold that you have to overcome to have, not to be sure, but to have a high probability that there is actually a damage. Then we use a damage indicator, which is based on, can be based on a physics, like the energy of the signal, the amplitude, or statistical, like root mean square variation, or correlation coefficient, and so away. Then we select basically all the paths among these that are really sensitive to a damage. And at the intersection of this point, we calculate, we interpolate actually the damage indicators that we have found. Another approach that is more local, that's a global approach. So you have a number of transducers, you try to understand what happens between all possible couple of transducers. Another more local approach, which is very important whenever you have a discontinuity to monitor, like a stiffener, because the stiffener, especially when we are talking about composite, they can detach from the skin. When they detach, the capability to absorb a load, especially under compression, is strongly reduced. So it's important also to monitor eventually the bonding. You can use basically, in that case, the stringer itself as a source of discontinuity by design, as I said before. So if you have a number of transducers alongside the stringer itself, you can use basically the reflection from the stringer, because whenever you excite a wave in a specific point, the wave is propagating in every direction. Not in the same way, because we are talking about composite, but let's say that it's propagating 360 degrees, and there is a direct path going to a receiver that is alongside the stringer, and there is an indirect path that is basically mirrored, more or less mirrored, because we are talking about composite, from the stringer itself. If there is specific condition for which the Snell law is actually valid and there is no mode conversion, you actually, the wave that is along the indirect path is really reflected from the stringer in a specific, is really mirrored in the mid place. What happens is basically that if you have a stringer like this, and you excite, so you are here, and you excite basically the wave that is going to interact with the stringer, and the stringer is correctly connected to the surface plate, actually part of the energy is going in the stringer and then is reflected back. So if there is the stringer, what I expect is part of the energy will be reflected back to the receiver. When there is a damage like this, you can see that this is a simulation of a debonding. The energy is basically flowing down. It's going on the other side. So what you expect is that if you excite away from this side, most of the energy, almost all the energy is basically going on the other side, and there is no reflection to the receiver itself. If you can simulate a condition in which you don't have mode conversion, so as I said to you before, there are different modes of propagating to the wave. So, and all these modes, they have different velocity, different characteristics, but there are some frequencies where you basically, if you have an antisymmetric mode, everything is reflected and transmitted as an antisymmetric mode. You know exactly wherever you expect to have the wave reflected to the receiver. So what you can do is basically something like that. So install a number of transducer. Then if you have a damage, you basically monitor, like you have a certain number of checkpoints, which are the mirroring points, considering all possible combination of transducer. You can window the time, the signal whenever you expect that the reflection is coming, because you know exactly which is the mode that is reflected back, and you can define a sort of damage indicator, basically comparing the energy of the signal that is expected to be reflected to the receiver itself. Let's have a look at which were the results that we got using this application. This is a demonstration from a European project called Tassaristu in collaboration with Airbus. This is the demonstrator is a outer wing box, and this is basically the lower panel of the outer wing box of a regional aircraft. There are 9 different impacts. It's fully full composite, and was basically the 186 piezoelectric transducers were installed on the structure. Piezoelectrics are used actually to activate the wave, because whenever you give an alternate tension at ultrasonic frequency, you basically create a deformation of the piezoelectric material that is transmitted then to the structure. The other way around, when used as a sensors, when the wave is propagating, is deformating, the structure is deformating locally, and the piezo is deformating and giving you basically a variable tension in time. So what we basically did, I just reported a couple of results. So first of all, we impacted in clear base, where what we expect, for instance, in this place is that you have a delamination. So there is an impact, the impact occurs, and there is a very visible impact damage, which is a separation between different plies. Whenever you have a stringer, you have a stiffening point, so there is a bonding between one component and the other. Whenever you have an impact, it can happen after a certain energy that the stringer is detaching. So we are talking about the bonding in that case. The lamination case is this one. We had an impact, basically, it's probably not very well visible, but there is a black cross, which is the impact location. This is the probabilistic imaging reconstructed by all possible paths that are intersecting together. And this is the same case where we had an impact actually under the stringer feet, so there was a delamination that was also validated by non-destructive inspection. Again, you can correctly localize using all possible combination of piezoelectric transducer. Let's move to the local approach. I already showed you before this plate configuration, still full composite for the same wing demo that I showed you before, but it's only a single part. What we did was basically to have the reflection considering the reflection coming from the stringer, window the signal, and having also then the calculation of the damage indicator. And this is on the right side is the results that we got basically here. So until this point, there is an LT area. The damage indicator is very low. This is basically noise that we are measuring, and is below the threshold that we also found out. Then there is an increase of the damage indicator, which is basically this area where there is a partial disconnection of the stringer. And then it's further increasing when we are in the central area, where basically this bonding was very clear. Again, the damage indicator is decreasing and then decreasing again. We compared this with the non-destructive phased array ultrasonic testing, and basically we got the same results. Of course, what we have is strongly different. Here we have one measurement every 15 millimeter, more or less. Here we have a more continuous inspection. It's more clear, and you can really understand what is happening to the structure. Just a comparison to give you an overview of other non-destructive testing that we considered. This is a chirographic image, which is very fast compared to non-destructive ultrasonic testing, but it's extremely unclear. So you can see the shadow here that something is not working as expected, but you cannot really understand what is happening. And again, there is a comparison between SHM and chirography is a confirmation, but you cannot really realize that something is different in the central area, like with phased ultrasonic testing. This is just a comparison to show you that SHM in this case was able actually to size correctly the defect, but the uncertainty that you have is totally different from an NDT testing. So the metrics that you have to use and the way that you have to use SHM is a little bit, is a good candidate as an alternative method of compliance to NDT, but you have to know that you cannot achieve the same sensitivity to damage detection. The idea could be that we are discussing also with some OEM is to use SHM as an alternative method of compliance and also to trigger also other NDT testing. What's the main challenge at the moment? All this, there are a huge number of actually methodologies that we have developed, also moving towards AI. The point is that whenever you want to implement something like this, you have to characterize the performance of your system. And this is one of the biggest challenges when we want to increase the, when we want to increase the, let's say, the TRL of our SHM system. First of all, you need a number of sensors. Whenever you need a number of sensors, you need to add mass on top of the structure, which is not massless at the end. Even if they are very lightweight, the transducer, you need some cables at the end as an impact on the aircraft design, which is not very clear from the beginning, but you have to understand how your aircraft is working. This is a cooperation with Flight Mechanics Group in Naples. What we found is that if you add a certain number of transducers and a certain mass of SHM system, what you have from maximum takeoff weight is an increase that is not properly linear versus the mass that you are really adding on the structure due to basically the snowball effect that probably all of you know. That's the reason why we found out that there is a limitation to have a break-even point. If you consider that there is a benefit having SHM on board, there is a limit of transducer that you can use. Otherwise, it's not any more economical viable. Also, there is, as I said, when we are talking about performance, we are talking about performance of the aircraft, but also performance of the system, SHM system. And one of the biggest problems is qualification. Whenever you qualify your NDT system, we started, of course, from NDT. Whenever you qualify, you are trying to understand which is the minimum detectable size of the damage, which is basically the standard damage that you can identify. Whenever we are talking about phased array ultrasonic testing, we are below 1 millimeter. So we are sure that we can actually detect very small damage. What about SHM? Whenever we want to qualify an NDT, we have to consider that there is an inspector, there is a part of area of the aircraft, and then there is an NDT method. Then there are some variables that we have to consider. When we are talking about the SHM is a solution that is part of the system, which makes everything more complex. We don't have always the same equipment. We don't have always the same staff that is, let's say, trained to work with NDT. So we have to understand how to use an approach that is well known as probability of detection. I will not, again, dive too much into the details, but basically, you have to identify all the variability sources that you have. And whenever we are talking about experimental test, we need to make some damage to a structure, which is not easy. You need actually a certain number of specimens to destroy every time and then test, which is extremely time-consuming and expensive. So we did, for this reason, a particular experimental test where we try to, this is again a composite plate with a stringer with different damage location and damage size. This damage was reversible, so there was a metal plate attached, correctly attached to the structure. We can simulate more or less in elastodynamics the effect of a damage within a climate chamber, so different geometry, different temperature. We try to compress some of the sources of data and sources of variability, and then we use it again. The damage indicators are, let's say, SHM metric. What we found out is that whenever you increase the damage dimension, the damage metric increase, of course, but strongly depends also on the path, so on the couple of transducers that you are considering. And the approach is basically that you have to plot and make the regression as linear as possible in linear scale, log-log scale, and then you move to basically a Bayesian approach where you can basically understand which is the noise around the regression and then build up the CDF curve, which is the probability of detection. On the probability of detection, you have then to found the confidence level at 95%. Then you find the probability at 90%, and the intersection gives you the A9095. This is one of the methods that is standardized for NDT, and we are now transferring to SHM to say, hey, this is my minimum detectable damage with the system I have. Of course, with the NDT, you have always the same equipment. With SHM, you have a lot of variabilities, which are coming from the structure. It's basically all is depicted here. You have a system that can change every time, and then you have the performance assessment. Everything is here is a source of uncertainty that you should basically elaborate. We try to elaborate some of them. What we found is that whenever you consider the distance of the path, so the couple of transducers make a path along the line of sight, there is a certain distance from the damage that you can see here, is here. This is the distance, this is the angle that the damage itself can make according to the shape. The effect on the POD is extremely different. This is a zoom in, and if you have a look at A9095 is distributed according to this distance from the path to the damage, which is extremely difficult then to qualify, because you don't know exactly which is the minimum dimension of damage that you can detect. Again, when you are considering path-based analysis, you have, again, the distance, and this is just highlighted from the different let's say, damage that we had at the beginning. There is an effect, a dominant effect of the distance. Here there is also a representation for theta, but there is not much actually effect of theta itself. Just to conclude, I know that was very fast and not very deep, but we can discuss later. SHM is a means actually to detect and quantify from the airframe, from a permanently system attached to the airframe, if something is happening in the structure, if something is changing. Something means something related that is dangerous, related to damage. Detecting SHM detecting damage using SHM based on guided waves is quite efficient. There are a lot of methodologies. As I said, you also moving towards AI-based learning approach, but it's very important actually to understand how to qualify this system to make them, at least for the short term, an alternative method of compliance to NDT. And the general POD analysis, which is what I showed you before, requires a big effort in showing really how we can understand which is the minimum dimension of damage that we can statistically detect. And it's extremely important to establish also a framework for cost-benefit analysis. So far, I am part of a SAE committee on structural integrity. Still, FAA and EASA, they don't want to give credit to anyone who is using SHM on the aircraft, which makes not economically viable an SHM solution. We have to understand also how to evaluate the economical benefit, and also basically understand, have a solid performance assessment approach where I know actually all the uncertainty that are playing around SHM, and they can be, how to say, qualified or quantified to make the qualification of the system itself. That's all from my side. Of course, I know that I was very fast and not giving a lot of details, but I wanted actually to show how we have to move actually in this time of application from the methodology to the certification aspect. Otherwise, wherever we apply something on the structure, that cannot be certified at a certain point is something like becomes only scientific valid, but not applicable. Thank you very much.
Okay, so thank you, Vittorio, for the nice presentation. So as we said before, now it's time for questions. So if you have any curiosity or something, you can ask. Okay.
Thank you very much for the very interesting presentation. Well, more than a question, it's a curiosity, because I work more on the vibration side, so vibration-based SHM. And of course, one of the main challenges is the sensor placement. Yeah. So my question is, what are the main challenges linked to sensor placement within this kind of SHM?
Okay, we need a couple of weeks probably to discuss all challenge. So we start from a specific idea that we want to detect as reliable as possible a damage. So the main challenge is actually how to place the transducer and to design the system itself, so from structural point of view, that can enclose the area that is critical for our site. So we can discuss a lot about global hotspot monitoring, so wherever you have some transducer all over the aircraft, but then at the moment the main challenge is to understand from the design which are the critical points, and then design around that problem an SHM system, which makes difficult actually to consider the sensor placement, because as I showed before, there are usually a couple of usable information coming from the wave modes and a lot of reflections. So if you don't place correctly, according to the also the edge and the discontinuity that you have, the sensitivity to damage could lower a lot. So the biggest challenge is actually to have, from my point of view, to have a good, let's say, simulation tool that can at least predict which is the effect of the sensor placement. There are some optimization algorithms around, but at the end, the next biggest problem from my side is connected, of course, also to our study that we have performed. You need a matrix, a certain number of metrics that you can use to say, okay, this is my optimal sensor position. POD is one of them. But then you need to really understand all the variables, because whenever you have, let's say, A1995 is a sort of statistical way to say, okay, in a statistically reasonable manner, I can detect this dimension of the damage. If you use this framework and you compare all possible sensor positioning, then could make sense to make a sort of optimization of sensor placement. But I would say that design of SHM system from also sensor placement is usually in our project was half of the project sometimes. So it's very, you really, it's very similar to the problems that I assume you have.
Thank you.
Okay, so any more questions from the audience? Okay, so I'll go myself. So what you delivered today, or some of the damages that you showed today, and how we can predict them by these waves, was mainly delamination, but let's say a visible delamination, like the one on the stringer joint, right, on the stiffener.
Yeah, it's okay. I get what you mean. This one, I guess. This one?
No, I think it's maybe one or two.
So this one is probably this one, because in principle they are not visible. This one?
No. I think it's ahead.
The stringer. So the stringer.
Yeah, the one with the simulation, the contour plot. Okay.
This one?
Yeah.
Oh, okay. Yeah, this is a simulation just to understand which is the physics behind, because we wanted to understand what happens if I have a debonding. And what we found is that basically part of the energy that was expected to be reflected actually is flowing. So we know that we will miss energy reflecting back to the receiver if we have a stringer the bonding. But in principle, all this damage are non-visible or barely visible. It means that usually you have an impact from this side. You know there is a debonding because we are talking about the specimen, but if you are in the wing box, for instance, you cannot see anything. And this type of, we found when opening the wing box, this type of debonding also on this here, for instance, if I remember, it was not here, not here. You see, especially when the impact occurs under the leg, so under the flange of the stringer, there is really a debonding that is, I mean, if you could be able to open the wing box, you could see very clear that this disconnected. There is really an area where it is connected. You can see it with phased array ultrasonics, but the problem of, that's the most important issues, it's actually, so basically if you know there is the impact and you touch in that location, you see that there is an indentation, but the indentation is among 100 and 200 microns, which means that if you just have a look, you cannot see anything. Even the painting would be not removed, actually.
Okay.
So in principle, it's defined as barely visible, but it's, I would say, not visible unless you really, you are a really expert inspector.
Okay, I mean, my question was pointing more towards trying to, or what could be some possible applications or enabling technologies that could allow us to do SHM, but even at a more microscopic level.
Okay.
So if you are envisaging some kind of technologies,
Like
some embedded fibers or something that could produce.
I got what you mean. I will say not for aerospace. I don't think there is this. No, it's okay. So if you consider this picture, this is basically the minimum detectable size at production. It means that everything is below this damage size is somehow accommodated by safety factors. So it's basically something, so from scientific point of view, it is possible. From engineering point of view, at least in aviation, according to the certification authorities and the, let's say, means of compliance they ask, it's not so important. Because basically during certification phase, you have to demonstrate that you can bear the ultimate load having a barely visible impact damage. Because they expect that there is a, they call detectability limit, below which you cannot see the damage itself. We are now working in that direction, so having more look to the microscopic damage itself. But I must say that this approach will never work because it's linear elastic waves based approach. We are moving to non-linear approach because when we are talking about linear elastic, we don't see anything related to non-linear propagation, which is usually affected by also grain size difference in the material or like embrittlement or anything is really microscopic. With this type of elastic waves, you cannot really see a difference whenever you have a microscopic damage. But if you have a microscopic damage, like one of the biggest problems, for instance, now is the hydrogen embrittlement. With hydrogen embrittlement, we are still considering also guided waves, but non-linear. It means that we try to, is a little bit different the way you activate the ultrasound itself, and you basically try to check if there is, if you excite at 100 kilohertz, for instance, you have a look at 200, 300, so the higher frequencies to see if something non-linear is happening in the material, because that's the one of the few approaches that work for very, very small damage. Otherwise, we are, with linear, we really need a discontinuity, because if there is no interaction with the damage, and the rule is usually that you can detect half of the wavelength of your wave propagation. So we are talking about 5 to 10 millimeters. Below that dimension is a little bit hard.
Thank you. I mean, I'm sure we can discuss later a little bit more on that. Okay. Any more questions? Okay. Maybe just the last one.
Thanks for your presentation. I have one question. Now we have a transmitter and we have a receiver that we are sending the signal. But the temperature or the homogeneous of the material can affect the signal that we receive on the other side for the resistor. How is this approach is sensitive to these parameters?
Okay, guided waves are very sensitive to temperature. So if you have 5 degrees difference, you see the difference. There is a phase shift, there is an amplitude shift, but this is usually compensated. So what is now the trend? In these experiments, I didn't talk about that, but you see here this one is a climate chamber. So we did the measurement at different temperatures, starting from 10 degrees, if I remember, to 50 or something like that. You see a phase shift, but it's easy to be compensated. And the error that you have, having a so you have a different possibility. Either you have a database according to the temperature, or you try to, let's say, interpolate among the different temperatures that you have. But in principle, the idea is that you always have a baseline information, so an interrogation where at different temperatures, you have a temperature sensor, like also, temperature is very important, but also pressure has an effect. So load, pre-existing load. If I'm testing the structure at different load condition, there is still a phase shift and an amplitude shift. The only way is to compensate. There are different algorithms that are based on stretching of the signal that they are working, or AI based as well. For this, learning approach are working very well. Welcome.
Okay, so there's no more room for questions. Thank you, Vittorio, once again for the nice talk.
Thank you very much.